Welcome. I'd like to present the paper Non-Random Weight Initialization in Deep Convolutional Networks Applied to Safety-Critical Artificial Intelligence. The running order is as follows. There's an introduction with the motivation, novelty and background. Then there's some challenges of the convolutional layer, a proposed method, some results, and then some conclusions. So as the motivation and novelty, we're interested in the area of artificial intelligence and safety-critical applications for dependable systems, and one of the issues that occurs around about that is the initialization state, creating variations in accuracy from learning sessions which are visible over regularization. The novelty that comes from the proposed method is we achieve a better accuracy than the random forms. It's robust to HE initialization. Accuracy that is higher is achieved first time, so therefore reduces development times, and it achieves lower loss during learning, so it learns earlier, which is less unlearning of the initial state, and perhaps enables smaller data sets. So the previous work looked at just perceptron layers in its form, and the first paper in that respect achieved an almost equal performance to the random forms, showing the viability of non-random forms. And then it was followed up using the Glorio-Xavier initialization limits with that form and achieved an equal score, showing that we can get an equivalence with a non-random form but with repeatable determinism. So therefore, Glorio-Xavier initializations and HE initialization particularly are of interest to us, as HE initialization is regarded as the state of the art. So what we can see in that previous work is on the left-hand side is the random weights after learning. We can see that they are diffused and random in nature, and we can see on the right with the non-random form that was used with the perceptron layers that there is a correlation between the pixel images and the number of nodes, and that the activations are in adjacent nodes, and therefore that is an advantage to rule extraction, as the generalization step is simplified as the activations are adjacent to each other. So what we wanted to do was achieve a way of doing this with convolutional layers, and we knew that the intuitions from the previous work wouldn't relate directly because they had the intuition that the fully connected layers of perceptron layers meant that the weight order wasn't important, and therefore the non-random initialization would be less complex than the convolutional layers because weight order sequence is important, and therefore we would need a new technique. So the test case that was used for this is the same test case that was used in the perceptron layers, but it's the convolutional version of it. And the first step towards that, because we're embracing the Glorio-Xavier limits, was to calculate all the weights and the image sizes, because they're calculated in different ways than the dense layer perceptron versions, and have inheritances. And so what I've done here is I've calculated the weights and the image sizes for every layer in the model. What we therefore do is then apply those sizes and calculate the limit values, which we will then apply our techniques within those limits. So what we wanted to do was have a technique that would have stripes and curves, because those are generally accepted as being important to filters, and they're also in tune with intuitions from Hubel and Weasel with experiments with spider monkeys under light anesthetic. And what we wanted to do was also have a number sequence which would allow us a number of filters, so that we could have a number of these forms that were different. And some previous work that we had conducted on least adjacency with shuffles seemed to have properties that could be quite attractive to this. So one of those properties that was quite attractive was turning vectors horizontally to vertical. And we can see here is a number sequence at the iteration 1, I think is in black, and then at the second or penultimate iteration before the vector length -2, which when it repeats at -1, has actually turned the vector into a different orientation. And that would therefore orientate our stripes in each filter. So what we can see here is the form is fairly simple in actual nature. What we do is we take the data set that we have, the addresses, we split them by 2 so that they've got gaps. We take the end half of the data set, reverse it, and put it into the gaps of the first end of the data set. And what we can see here is that it can be applied iteratively, and that it will actually repeat the sequence at vector length -1. What we might also notice is that the first element in the vector was unchanged and didn't move. That wasn't really important for the shuffles, but it would be an importance here. So what we do is we alternate the direction that the vector is placed before we use them, and that doubles the number of filter permutations as well. We did try some other experiments with directions and pre-shifting and pre-scaling. Those all seem to be not as effective. However, what we also wanted to do is within those addressings, the values within those, we experimented with different number sequences like the linear ramps and the sinusoidals, like we had experimented in the previous work in perceptron layers. And what we found was sinusoidals actually provided a better result in the convolutional layers. However, the last layer, which was a dense layer, still retained that intuition that the linear ramp was of benefit there. So that was the highest score. So what we can see here is actually looking at some of those number sequences. We can see the filters here. I think there's 32 of them in this particular model. And between the random and the non-random form, what we can see is the non-random forms are more striped and the random forms are more speckled. We can see that there is a dominance before learning to after learning, which has that. And if we subtract the difference between them, we can see that in actual fact, the result of it is actually fairly similar. In actual fact, we would say equivalent, but in actual fact we know the performance is better from the non-random scheme. And the reason for that is this form actually induces earlier learning. It has less unlearning of the previous state. Therefore, more of the data set is used earlier. And what we can see is that at batch 100, that the loss has reduced to a lower value quicker in the non-random forms, and is around about 1.75, and in the random forms is still getting going in the learning of the unlearning of the initial state, and is around about 2.0. We can also see that that effect is the same whether we use the shuffle or the non-shuffle. Remember, this is the first epoch after learning. So then what we wanted to do was check to see if this form would be robust to HE initialization. We didn't use HE initialization right from the start because the baseline value, which had the baseline model, which had been optimized with HE initialization, it would have been unfair to just switch that to HE initialization and then use other forms without some rigorous optimization stage. So what we did is we checked for HE initialization robustness, and what we can see that in every case, in every shuffle, iteration, and in every epoch, that the value in actual fact has benefited. And what we can see is the best benefits come in the first epoch, which is what we might expect because that is the epoch after learning, and therefore it would have the benefit of that extra learning earlier. So in terms of what we achieved a higher accuracy. In actual fact, in the first epoch, it's around about 2.8%, which is certainly worth having. Over the entire data, over the entire epoch of the models, it diminished down to about 0.5, but it's still positive. And what we could do is we achieved that result the first time. There was no variation in the learning sessions, so that saves development time. The accuracy was repeatable and deterministic, which is a value of dependable systems, and it achieves a lower loss earlier, and therefore is using more of the data set with less unlearning of the initial state. That could perhaps reduce data set sizes as well, although perhaps more technically it is actually using more of the data set more effectively. Thank you very much. Do you have any questions?